We are rolling.
Oh, action. Welcome to segment number 3 of Calculus in the Real World. Half-life of elements that no one has ever seen. Do you notice that when we talk about decay of elements, it's like radium or polonium or plutonium or things that no one's ever seen in real life? I'm wondering if the scientists just made them up. So if any of you become physicists, chemists, that's the right word, please tell me if they're actually real, because I would love to know. But world lesson right now is that we're sitting in front of my TV. I will show you how often I use my TV. I usually do things like this. It's a very good prop up for, doing mathematical things. So, TV is not the world, people. I just want to let you guys know that. But here we go. Half-life of elements. I remember we struggled with this a little bit when we reviewed it at the beginning of the year. Talking about it with differentials makes it a lot easier, because our equation that we're going to get used to is going to be y equals y naught e to the negative kt, alright, which we just kind of solved with it's all about the money, getting from, if something decays or grows at a rate proportional to how much is already there, it's always going to end up looking something like this, because you've got the rate, you end up having an e because you have the natural log, and this is always the initial amount. And it turns out as long as you have two of these things, you can always find a third one, alright? Or you can always find another one, because we know the rates are going to be proportional. So the question that we're going to be answering right now is, what is the half-life of radium-226 if its decay constant is 0.00436? Now you may be sitting here thinking, we only have one number. This is true. We have the decay constant, alright? So if I plug that in, I've got y equals y naught e to the negative 0.000436 t. But we actually do have the rest here, because we know we are looking for the half-life, alright? So we take the amount that's already there, and we just want to know what is half of that going to be. We want to know basically the time that it's going to take for this thing to cut itself in half. So the nice thing is then we can basically just take this right here, plug in y naught over 2, because that's going to be the half-life of what is originally there, equals y naught e to the negative 0.000436 t. You guys are very, very smart calculus students, so you know what's going to happen to this initial amount right here. We can just divide it out on both sides. Get rid of it. We're going to be left with 1/2, alright, is equal to e to the negative 0.000436 t. And as you guys know, we can take the natural log of both sides, and we are going to end up with the natural log of 1/2 equals our constant times t, and we divide by that constant, and we are going to be able to get t equals, and I believe in this case it is right about 1,590 years. Now here's something that's going to be super helpful. I'm going to say it right before we would maybe put this example to rest, is there's going to be something that's really nice to notice about half-life. If you guys notice, since the initial amount divides out, it really has very little to do with the initial amount. It all really has to do with the constant that's going to be here. So, if I come over here, kind of an important lesson to learn is no matter what our initial amount is going to be here, we can always find the half-life. It's going to be the natural log of 1/2, alright? Let's just leave the k in here for a minute. Let's just pretend we called this negative kt, alright? The half-life, which is right here since we talked about it being divided by 2, is simply going to be this, alright? The natural log of 1/2 over negative k. Alright, that's going to equal the half-life. But let's for a brief minute talk about what we know about natural logs, alright? When we have 1/2, we can write that as what? We can write this as 2 to the what power? Well, if it's on the bottom, we can write it as 2 to the negative first power. Well, using your log properties, we can bring this out front. So this will be negative natural log of 2 over negative k is equal to the half-life. And these negatives just cancel right out. So the half-life is going to be equal to the natural log of 2 over the decay constant every single time. So that might be a useful thing to write in your notes before you try your homework problems on your own. And I'll let you at it. good luck with your half-life of elements that no one has ever seen.